Hey, welcome back to Linear Algebra. We're going to get started in section 2.2 here, looking at what's called the matrix of a linear transformation. So in section 2.1, we defined what we mean by a linear transformation. We looked at a couple of important relevant subspaces, the null space and the range, the image. And the dimension theorem relates the dimension of those subspaces to the dimension of V in the case that dimension of V is finite dimensional. So in this section, we're going to kind of move towards what we'll call a matrix representation of such a thing. So I want to define a couple of things in here. I'm going to first talk about an ordered basis. We already know what I mean by a basis for a vector space, but we'll define what we mean by an ordered basis. And once you have an ordered basis, inside of that basis, or with respect to that basis, every vector has a so-called coordinate vector. So I want to tell you what those things are. And then I want to give you a recipe for how to make the so-called matrix representation of a linear transformation with respect to two ordered bases. It's a mouthful. There's a lot of ingredients in there, but I want to show you it's a very algorithmic procedure you can follow. So I want to try to make that procedure very clear, hopefully illustrating with examples that keep us all interested in what we're talking about. If I fail to mention it, everywhere in this lecture, V is a finite dimensional vector space over F, okay? So V, I'll never denote by anything but V, a vector space. Our field F, take it to be the real numbers if you want to. And what I'm emphasizing here is that if I don't say otherwise, I always mean it, that V has a finite basis. It's a finite dimensional vector space, okay? So let's get going here with our definition. So you know what a basis for a vector space is. A basis is a linearly independent spanning set. So what do I mean by a so-called ordered basis? Well, an ordered basis, beta, I'll use the same notation, it's just a basis, V1 to Vn, together with a specific ordering of V1 to Vn. Okay, and I won't invent any new notation when I write an ordered basis like this. It's understood that the element that I write first is in position 1. The element that I write second is in position 2, and so on. And when I'm talking about an ordered basis, I'll never change those things. I'll never change their order. All right. I think the most standard, the standard normal basis of the ordered basis that you know of is the usual basis, the standard basis for Rn. So you guys remember here that E sub j is a vector, all of whose coordinates are 0, except for 1, 1 in the jth component. So we order that basis by putting them in the order where j increases from 1 to n, okay? Another basis we've been using for the polynomial space, polynomials of degree less than or equal to n, is the monomials of degree 0 up to n. And we'll order them in that order. Okay, so when we're talking about an ordered basis, I think of this as the first thing, the second thing, and so on, the nth plus first thing. P has dimension n plus 1. So that's all I mean by an ordered basis. I mean, write down a basis, notice the order that you wrote the basis vectors in, keep them in that order. All right? So if you like, as a little combinatorial problem, I'm going to leave it, I'm not going to answer it here, but given a basis, how many ordered bases can you make from it? So how many distinct ordered bases? So if you change the order of the elements, you've changed the ordered basis, even if you're using the same thing. So there's a little fun combinatorics problem you can ask me about. Okay. So moving along here, what do I mean by the coordinate vector? So you give me some ordered basis, okay? So beta is an ordered basis for my vector space V. Then when you give me a vector in V, because beta is a basis, there are unique scalars, A1 to AN, that you can write V as that linear combination, right? And since we have agreed that beta is an ordered basis, these scalars would always come in the same order. So if we arrange them into a column vector here, like I've done in the middle of the page, putting in the first row, the first coordinate scalar, the second coordinate scalar, and so on, I get a column vector in Fn, and that vector I'll call the coordinate vector of V with respect to beta, or just for short, because that gets to be a mouthful, I'll just call it the beta coordinates of V. Okay, so the scalars themselves are uniquely determined by beta, And if we agree to never change the ordering of the vectors in beta, then for a given v, all of us would write down the same column vector. So that's what justifies calling that column vector the coordinates of v. So it's sort of how we understand v in that particular basis. Okay, it's the coordinates of v with respect to that basis, or just the beta coordinates of v. Let's look at some examples. You take any ordered basis in the world, take any ordered basis in the world for your vector space, and you wonder, what are the coordinates of the ith basis vector with respect to that basis? Well, you get the ith standard basis vector, right? Because VI, you want me to put in some details here, VI is 0 V1s, 0 V2s, 1 VI, 0 VI plus 1s, and so on, 0 VNs. So all of the coordinates are 0 except for the ith one, it's just EI. So EI is kind of what VI looks like in coordinates with respect to the basis beta. Okay. How about like in a polynomial space? Polynomial space, say polynomials of degree less than or equal to 2. Let's take the ordered basis 1xx squared. Well, we'll always use that ordered basis. Then if you give me a polynomial, like 3x squared plus 2x minus 1, and you ask me, what are its coordinates with respect to beta? Well, using the ordered basis, can you see that I'm using minus 1 of the first basis vector, so I put a minus 1 right there. And then I'm using 2 x's, so 2 goes in the second spot, 3x squared, so 3 goes in the third spot. So in this ordered basis, this column vector, negative 1, 2, 3, is my coordinates of my polynomial vector, 3x squared plus 2x minus 1. And the point is that if I understand the ordering and I know what the basis is, from this coordinate vector, I can recover the polynomial and vice versa. So in some sense, they're kind of the same thing. This is sort of an encoded way of writing down that polynomial, right? And you understand what I'm talking about as long as you can decode. Like if I gave you, say, turning it around, if I said that the beta coordinates of some polynomial are, I don't know, 5 minus 11, 13, then you can tell me what the polynomial is, right? Because 5, well, that's the coefficient of the constant term. Negative 11 is the coefficient of the linear term. 13 is the coefficient of the quadratic term. How do I know which one goes with which? Because it's an ordered basis. Cool. We'll take up the problem. I don't know if I have room here. I don't have a room there, but we'll take up the problem of like, well, given a vector in a vector space, how would I write it in a given ordered basis? That's an important problem in linear algebra that we'll tackle when we get into chapter 3. Okay, so right now I'm just kind of establishing what I mean by coordinate vectors. Okay, here is the main definition of this lecture. I would like to be able to write a matrix down associated with a linear operator. So here is the definition. I'm not deducing this, I'm defining it. It's a little busy, but I think you'll get used to it. So given some linear operator from one vector space to another, take a basis for V and a basis for W, calling them beta and gamma. Okay, that's the Greek letter gamma. So the basis for the vector space V, I'm calling V's. The vector space W's basis are called W's. You can see in my notation, V has dimension N, W has dimension M. Okay, because those are bases. And in particular, they're ordered bases. Cool. Okay, so for each j between 1 and n, for every one of those values of j, because it's a basis, this is my notation for there exists unique. So you read this, there exist unique. So the exclamation point means they're unique. There's unique scalars. And this looks really busy, right? Why all the subscripts? Well, because there's m scalars. So I need one subscript to be counting up to m. but these are all for some fixed j. So the j is just reminding me of that, right? So there's m scalars, a1j, a2j, and so on in my field, so that when I take t of vj is an element of w, so I can write it as a linear combination of this w basis. That's all I'm writing here. The aij's are my scalars. They exist because the w's span. They're unique because the w's are linearly independent. Okay? So there are unique. So in that notation, all I'm saying with respect to the above, the gamma coordinates of t of vj is this column vector, a1j, a2j, and so on. Okay? So I have one of those for every one of my n basis vectors. So take those things for each j and make a matrix. So this t beta gamma is a matrix. This matrix will have m rows and n columns and elements in F. And what is the ij entry of the matrix? It's aij as defined above. Or if you like, for the first basis vector, I write it as a linear combination of my w's. I find its gamma coordinates. I make those coordinates the first column in my matrix. Then for the second basis vector, find its coordinates, make them the second column in my matrix, and so on. Okay, let's just make sure that this dimensions make sense. These column vectors, how many of them are there? Well, there's one for each vj. So there's n columns. That looks right. How many rows are there? Well, the rows is the length of this column vector. There's m of them. So it's an m by n matrix. And it's got a long name. It's called the matrix representation of T in the ordered bases beta and gamma. This is the notation for it. Okay, so to explain the notation, it's supposed to help us. T is the name of the map. It's got to be in there. These brackets remind me that it's a matrix. Okay, the distinguishing between T and its matrix. The beta and the gamma are the bases for the domain and the codomain. Why is beta a subscript and gamma a superscript? Well, I don't know. That's one of the mysteries of the universe. But the notation just includes the ingredients. Function's name is T. I'm making a matrix. I'm doing it with a domain basis gamma, beta, and a codomain basis gamma. Nice. Let's practice this. Oh, sorry. If V and W are the same and beta and gamma are the same basis, we shorten the notation. I just write T beta instead of T beta beta. Okay, so that's just kind of a notational convention. So if you see one of these matrices, T is a function, so I won't confuse it with a coordinate vector. And if it looks like it's missing something up here, it just means V and W are the same. There was just one basis. Cool. Let's do some examples. This isn't quite like our example from section 2.1, but it's similar to it. So I've got a vector space R2 and a vector space R3. Here's my linear functions definition. T of AB is, you can look at it, A plus 2B and so on. So you can see the 3 coordinate functions, yeah? And I'll leave it to you. It's an exercise. T is linear. I'm not gonna put in the details here. I'm gonna choose these 2 bases, standard basis in both spaces. Okay, so beta is E1, E2. Over here in R2, what do I mean by E1? I mean it is the, I'll write them as column vectors, 1, 0. E2, 0, 0, 1, 0, 1. This E1 over here in R3, I mean 1, 0, 0, right? Or if you want to write it as a row vector, 1, 0, 0. How do I distinguish them? Context. So look, I'm denoting them both by E1. I just keep track of what E1 I mean by asking myself, is it in the domain or the codomain? Cool. So I worked some of this out ahead of time. You should probably pause the video, but using the formula for T, T of E1 would be 1, 1, 2. Yeah? Why? Because if you plug in, I'll just do it with the laser pointer with you, 1, 0, Okay, well, you get 1 plus 0, 1 minus 0, 2 plus 0. Well, that's 1, 1, 2. And likewise, pause the video and check that t of e2 is 2 minus 1, 5. So then I'm going to take these things, take this 1, 1, 2. Well, and if I write it as a linear combination of the basis vectors over here, it's 1e1 plus 1e2 plus 2e3s. Yeah, 1, 1, 2 is that linear combination of the standard basis vectors. So I take those coefficients, 1, 1, and 2, and I put them in the first column of this matrix. 1, 1, 2. Does that make sense? Likewise, 2, 1, 5, that's 2e1s minus 1e2 plus 5e3s. So I take the numbers 2 minus 1 and 5, and I put them in the column of the matrix. What do we do with this matrix? Well, I'm going to tell you about that, but right now in this video, I'm just focusing on how to construct the matrix. So somehow this matrix encodes all of the information we need about the linear transformation, but that's coming later in our story. Okay, let's look at another one. Let's take the differentiation operator. I'm calling it T here. I called it D before, but here's how it works. T of a polynomial is the derivative of that polynomial. Okay? Standard basis for the domain and the codomain. Polynomials of degree less than or equal to 3. It's 4-dimensional space. Polynomials of degree less than or equal to 2. It's a 3-dimensional space. What do I want to do? I'd like to find the matrix of T with respect to these two ordered bases. Okay? I can tell you that it's going to be a 3 by 4 matrix, right? It's going to have 3 rows and 4 columns. So let me actually make some space for it right here. Make 3 rows and 4 columns. And then how do we fill it in? Well, you have to take T of, say, your first basis vector. So T is the derivative map, right? So I'm looking at this first basis vector, 1, and I'm taking the derivative of it. Well, the derivative of 1 is 0. If you're going to write 0 as a linear combination of these polynomials over here in gamma, you have to take all the coefficients to be 0. Next basis vector is x. T of x is 1. All right? When you write 1 as a linear combination, here I'll write out the details. It's 1, 1 plus no x's plus no x squareds. So I'm going to take those coefficients, 1, 0, 0, and make them the next column. Is it making sense? T of x squared, derivative of x squared is 2x. 2x is 0 ones plus 2x's plus no x squareds. So I'm going to take those coefficients, 0, 2, and 0, and make them the next column. Finally, t of x cubed is 3x squared. 3x squared is no ones plus no x's plus 3x squared. So the last column is going to be no ones, no x's, 3x squareds. So there is the matrix of the differentiation operator with respect to these bases. We'll do some pretty cool stuff with these matrices, but right now I'm just focusing on how to find them. Okay, pause, digest, think. I'm going to do one more. This one's going to look a little bit weird, but I'm going to take the vector space V and W to be 2 by 2 matrices. Okay, and my ordered basis beta, I wrote them right there. It's a 4-dimensional space. Those 4 matrices define the 2 by 2 matrix, or make a basis for 2 by 2 matrices. And I'm going to order them in this way. I'm calling them E's, putting a subscript for where the one and only non-zero entry occurs. And I'm going to order them kind of, I think of it like dictionary. So they're ordered by row and then by column. Okay, so E11, E12, E21, E22. And my function, tau, is that Greek letter. If you don't already know it, this is the Greek letter tau. Just a temporary name. Tau of a matrix is its transpose. Okay, I'd like to find the basis, or the matrix for tau in this basis beta, which I'll just write once because the codomain and domain are the same space and I'm using the same basis. That matrix should be 4 by 4. It's going to be 4 by 4. And to compute its entries, well, we need to take, say, tau of the first basis vector. So transposing E11, you get itself. So when you write that as a linear combination, that's 1 E11, no E12s, no E21s, no E22s. Sorry, that's squeezed in there. So the coordinate is tau of E12 is E21. When you transpose this matrix, flipping it across its diagonal, you get that one. So E21 is a basis vector, right? So its coordinates are no E11s, no E12s, 1 E21, no E22s. So I'm actually going to leave it to you to check that the rest of this matrix would look like this. Okay, and you can ask me about it or we'll explain it in class. Okay, so that wraps it up. Let me just swing back up to the beginning to make sure we did everything we were supposed to. I was trying to, in this lecture, define an ordered basis and the coordinate vector of a vector in a given ordered basis. I wanted to define the matrix of a linear transformation. We did it. And I wanted to illustrate computing that matrix with examples. We did it with 3 different examples. Okay, thanks for listening.